Well, in this video I want to talk about doing a calculus max-min problem. The example I'm going to look at involves constructing this rectangle here with two vertices on the graph in red of a parabola and the other two vertices on the x-axis. We want to do it in such a way that the area of the rectangle is going to be maximized. It's called a max-min problem or optimization problem. So here's the statement of the problem on the screen that I just described. The actual parabola equation is y equals 9 minus x squared. And I've labeled here a point on the graph of the rectangle as the point xy. So if I'm at this point, the x value is x, y value is y, which would be 9 minus x squared. And what we can notice is that the area of the rectangle would be, like a length times a width. And one of the dimensions, say this one here that I'm indicating with my cursor, would be of length 2x. If this point right here has where x is positive, has a x value of x, then the distance from here to here, based on the symmetry of the graph of your parabola, a nice even function, that distance will also be x, the positive x value here. So 2x would be that dimension of the rectangle. And the other dimension, distance from here down to here, is whatever the y coordinate is there. So as a function of x and y over here, that area is in terms of x and y, if you one dimension 2x times the other dimension y, and since y equals 9 minus x squared, and the x value here is the positive value for x between 0 and 3 corresponding to this point. So 2x times y being 9 minus x squared gives us this area of the rectangle as a function of x, for x between 0 and 3. Now we know that the maximum value for this function is a nice continuous function, so it's got to have a maximum value for x between 0 and 3. And it either has to occur at x0 or at x3 at one end of the interval, or at a value for x in the interval where the derivative, the calculus derivative, is 0, or if it could be undefined. But this function here is what's called differentiable everywhere, so the only possibility would be derivative 0. So if we compute the derivative of this function, it's 18 minus 6x squared, set it equal to 0 and solve for the positive value for x between 0 and 3 that satisfies that equation. Well, that equation tells us that x squared would have to equal 3, and then x is the positive square root of 3 for positive x. So our candidate for the maximum area will occur when x is the positive square root of 3. Other possibilities are 0 and 3, but if you think about it, at x0 or x3, either that factor or that one in the area function will be 0, and so the area will be 0. So your maximum value for the area must occur at the x value of square root of 3. That's the only critical value, is called value where the derivative is 0 in the interval from 0 to 3. And we could also compute the second derivative, negative 12x, which would be concave down, negative concave down for x positive. And that second derivative at square root of 3 is a negative number, so you had to have a relative maximum at the point on the graph of the area function where x is the square root of 3. And in fact, we get an absolute maximum area of the rectangle for that value of x. then the dimensions that will maximize the area will be 2 times the x value for one dimension and the y value of 6 when x is square root of 3 for the other dimension. And that maximum area would be exactly 12 times the square root of 3 square units, approximately 20.7846 square units. We can visualize what's going on here if I look at the next slide. What we have here is an animation that shows various inscribed rectangles here in this parabola. And over here is a shifted area function. The area function is actually function with x going from 0 to 3. This has got to go from 4 to 7, so I just shifted the area function over, but it does correlate. And what we know is going to happen is when this animated point gets to the high point on the graph of the area function, that's going to indicate the value for x there that will produce the maximum area. So if I actually stop the graph right up at this point, you can look at the shape of the rectangle that gave you a maximum area. In fact, if I go over here and click in this little MP4 video, within the video, I can actually do that. I'll just stop it up here, try to stop it. Just move it back a little bit here. Actually, you can click in here also and actually get the point to correspond to where you're clicking. So I've got it clicked there, just about the high point on the graph of the function up here. It may not have clicked perfectly, but that's probably better. Okay, so that looks pretty good. So here we got the animated point stopped at the high point on the graph of the area function, and you can see what the rectangle looks like that gives us a maximum area. Now we don't have a perfect scaling on this picture, but it's pretty close. On the y-axis from here to here is 5 units, and on the x-axis from here over to about here would be 5 units, and about the same distance. So pretty accurate picture of the rectangle that gives you a maximum area. One over here a bit actually doesn't, as we can see from the area function. So oftentimes you think a square is going to give you the maximum area, but not when you're inscribed in this parabola like that. The square didn't actually give us the maximum area. Maximum area was dimensions 2 times the square root of 3 by 6. This was up here a bit. Let's just take another quick look at it. About look about like that. Well, still kind of a dangerous world out there, all kinds of places, all kinds of ways. So I hope everybody watching me here, watching today, stay safe.